very much. Thank you very much to the organizers. I'm glad to be here and to give a talk that it's maybe somehow far from what has been told in these talks before, but well, I would like to present these results, and I am going to talk about two things that go together. These are the foliations that are induced by vector fields that have that are degenerated vector fields, have an isolated singularity, but do not have a linear term. These foliations were studied long ago, and it was René Thom who wanted to know about the invariants, the analytic invariants that classify this kind of foliations. So I am going to talk about this, and also I will be interested in talking about the analytic classification of curves that are singular, but that have well, in the moment I would say they are several branches that are smooth, and I would like to relate these two aspects. So let me begin with the foliations. The classical statement for foliations are those that have linear terms. Those foliations were well studied by Poincaré, by Siegel, Bruno, and then by Martinet, Ramy, Moussu, Takens, Frank Loret, and all these things were where the vector field that defines the foliations has linear terms. Now, what I am going to talk is about the foliations that are defined by a vector field x point, y point, v xy, where v xy is given by analytic terms. These are homogeneous polynomials of degree n, n plus 1, and so on. And the other term are qn xy plus 1 xy, and so on. And we are dealing with a complex parametrization. So we will have Riemann surfaces, and we would like to give the analytic invariants. So one thing to look at is this polynomial that is defined, homogeneous polynomial, and defined in this way, Qn y Pn xy. This polynomial allows us to make two cases, completely different cases, and are given in this way: Rn plus 1 not identically 0, and Rn plus 1 identically 0. These two cases give us two completely different type of foliations, and this one will be the non-diacritic case. And this will be the diacritic. And I will denote the induced foliations by a vector field V as FB. Before talking about the geometry that is behind, let me give the definition of equivalence, analytic equivalence. So we will say that, let me put it here. If we have two vector fields, I am going to be all the time in C2, 0 germs of vector fields. So if we have one vector field, let's say, let's put it like this, big C, and the other big C. We have here the vector fields and have the solutions, the foliation that is induced by the vector fields. We will say that they are analytically equivalent. If we can find a biolomorphism, a local biolomorphism, that sends the solution, let's say BTP, it is sent phi T phi B TP to the corresponding solution that is in HP of this equation. So it will be W T HP. This is the equivalence of vector fields.
Is H time dependent?
Is H what?
Time dependent. You have H of T.
H of
T.
T. H of sorry. Thank you. Thank you. So this is when we are interested in vector fields. But if we are only interested in foliations, then we allow the time to be different. Or what we can say is that the push forward of the vector field V will be a function multiplying W. So this is one thing. And we are going to work with strict equivalence. So we will ask the derivative of H to be the identity. Well, so in that case, we say that the foliations are strict orbitally equivalent when we say this. Okay, so I return to the non-diacritic and diacritic case. When we have a non-diacritic foliation, we will have the following situation. We have xy, and we'll have some curves that go to the origin. Let me put some curves. Okay. And the other ones do not touch the origin. So we have only a finite number of curves of the foliation, that go to the origin. There are the separatrices. And if we make what is called the blow-up of the singularity, then we will have that the sphere that we get from this point will have some marked points that correspond here to the tangencies of the separatrices. So, and in that case also, we have that this sphere is a solution of the equation, is invariant by the equation. Well, for the moment, let me put Pj, P1, P2, and so on. So the tangencies here are seen in here. I will say other things later, but for the moment it's here. And this is the non-diacritic. Foliations. And for the diacritic one, we will have again our xy, and we will have the curves doing something like this. Let me. And we'll have here one special solution. We have the singular point, and the other curves, I don't want here to make a lot of leaves, but we'll go like this, and we can have another loop like this here, whatever. And when we blow up, we will have the sphere, and here we'll have this direction that I will call QJ, and we will have that the tangencies, you can make here a line, the tangencies that are y equal to ux, and the other one, I cheat myself like this. The other one will be y equal to u star x, and these are here reflected. Here is the point, is the sphere, yes, and we have one point, the point Qj, that will be a point of tangency with the sphere. And the other leaves cross the sphere. Here I will have the point U, and here the point U star. So we will have here define a natural involution that is defined in the sphere associated to this tangency point. So we'll have I, Q, J, the involution that is associated to this point. We can have other curves here, tangency curves, like this. Q, K, and the corresponding involutions. Okay, so, well, and here we have the leaves that cut. We can have more tangencies, and correspond to leaves that go here in this way. Well, so they are completely different situations, geometrically different situations, and we would like to ask Tom's question about the analytic invariance. So some years ago, with Sergei Voronin, and Ernesto Rosales, we answered to these questions for both cases. For the non-diacritic case, let me talk first about the non-diacritic case. There is a natural transformation that it is called the vanishing holonomy, and it's given in the following way. We have here these lines that go here are separatrices that cross the sphere. Well. And the rest, the other solutions do not touch the sphere. So they are going like this. In the generic cases, one can have some type, Poincaré type solutions, and one can know what happens around in the neighborhood of the sphere, outside and inside. No problem. And we can take a point that is not a singular point, put a local transversal to the sphere, and now we can take loops surrounding these singular points and look to the transformation here that goes. One take a point and we lift the loop to the solution. So we have a transformation that goes around the singular point. It can go around the sphere, no problem, and returns. So these transformations are the holonomy maps, and we have defined in a natural way a group, the holonomy, the vanishing holonomy group, generated by the holonomy maps. So for generic vector fields, if we begin with n of course bigger or equal to 2, we will have, for generic cases, n plus 1 singular points, and so we will have n plus 1 holonomy maps, and the group is generated by n, because we are in the sphere. And we can consider the class of analytic equivalence of these maps. This class I will denote in this way. And moreover, well, first some words. Tom make the conjecture that these separatrices and the holonomy that was seen in this open, in C2, were the invariants, the analytic invariants. But very, in a short time, Mousseau rejected this conjecture and looked at the vanishing holonomy, the one that appears when we make the blow up, was needed we need to regard to this holonomy and not here. There is something that is hidden, so we need to look to this holonomy. And Mousseau could prove the conjecture for the cusp, but it was false in general. So the invariants were unknown, and finally, with Voronin and Ernesto Rosales, made the following thing. We took the formal normal form. We make formal transformations of these vector fields and get the simpler one in some sense with the formal transformations. And this formal normal form can be written for a vector field like this, like AB. This is BC. This is V0 plus BC plus VB. So the vector field V will be transformed to a vector field that has the principal part, Pn, Qn, plus some Hamiltonian vector field, a finite number of parameters define this Hamiltonian vector field. Let me write it like this: Hamiltonian vector field with a finite number of parameters and a radial vector field. Now, but this is formal, okay? So this Hamiltonian vector field has a finite number of invariants, the coefficients, and I will denote it like this, the coefficients. And they are, for n, they are n minus 3, n minus 2 over 2. And Thom's invariant will be the following. We define tau v to be the collection of complex number from here and the conjugacy class of the holonomy. So what we proved is that two vector fields V and W are strictly analytically equivalent, but orbitally. That means that we look only for the foliations, if and only if the tau V is equal to tau W, when W has also the principal part. We fix the principal part. This principal part fixes the singular point and fixes also the linear part of the holonomy maps. So in the generic cases, we ask for holonomy maps that have linear part such that the eigenvalues are not rational numbers. For rational numbers, everything is broken. Okay, well. On the other side, well, we proved that these invariants, given the invariants, we can always find a vector field that realizes them. This is also one thing that has to be said. For the dicritic case, the things go more or less the same. we will have a vector field B and its formal normal form. This formal normal form will be somehow different. It will have, at the beginning, it will have a radial vector field, and this radial vector field is a product of y, q, j, x, j equal to 1 to m, and this has to do with these points, these tangencies, plus some vector field with finite invariance. I'm not going this, well, not need to put it, but it will be also C tilde ij, a finite number of invariants, plus something that is not convergent. So in this case, the Thom's invariants are the collection of finite number of parameters and the involutions for which it is needed to the collection of involutions for which it is needed to fix a parameter on these involutions. But it's technical, something technical. So again, two vector fields, diacritic vector fields, are analytically equivalent if the Thom's invariants coincide. What is somehow amazing, well, we didn't know the meaning, the geometric meaning of the finite invariants. We really still don't know about the geometric meaning in both cases. And we are looking for this geometrical meaning. But something that is somehow amazing is that when we make the construction to give these invariants, we needed to construct an auxiliary foliation that is dicritic. For the non-dicritic, we needed to construct a dicritic foliation. And when we analyzed the dicritic foliation, we needed to construct a non-dicritic foliation. So they work somehow as a pair of things. So we looked for, something that has to be said. When we have these tangencies, there are avoidable tangencies and tangencies that you cannot avoid. So what we looked is that, when you intersect the dicritic foliation with the non-dicritic one, you will get some curves that are called curves of tangency of one foliation with the other, or polar curves. So these curves are in some sense natural of this foliation, and when you take the number of parameters alpha, number of parameters of Cij, and take the number of parameters of the corresponding foliation, number of parameters beta, and you make the sum, alpha plus beta. This number, when n, this was m. When m is equal to n minus 3, that is the minimum that you get from these curves of tangency, the sum from this and this will be 2 n minus 1. And this number, no. This sum is the dimension of the moduli of 2n minus 1 singular smooth branches. So, it is clear that the separatrices are not Thomson invariant. This is clear. There are not enough. With these constants, you can construct the curves, the separatrices, to realize the invariance. But there are not enough. You need to add to this to the separatrices something else. But the thing is that if you take alpha, this number, and this beta, it is the moduli of 2n minus 1 curves that cross transversally, pairwise transversally smooth curves. So our next step was to look if one can realize the analytic classes of curves that are pairwise transversal and have n plus 1 branches. So this problem, So the problem was the following. Can we realize a singular curve given by n plus 1 smooth branches as invariant curves of a diacritic foliation with a given collection of involutions. That is, we would like to know if we can realize by means of a diacritic foliation any kind of smooth, n+1 smooth branches in the origin, the analytic class of these smooth branches. If we can realize it, given a collection of involutions. Yes? And the answer, this work with Jessica Jaures. The answer is that we have that M, for M less than n-3 in this setting that I am talking about, is a very flat set. For M equal to n-3, one can realize almost any class of any analytic class of curves with n+1 smooth branches inside a diacritic foliation with prescribed involutions. This can be done in an open-dense set. And if M is bigger than n-3, then we can freely always realize these curves. And what is important for us to do so? Because Zariski asked in 1973, asked for the analytic invariants of singular curves. Those analytic invariants are already known for one branch. This was done by Abramo Jefes y Marcelo Hernández. And they succeeded to give the analytic invariants for one branch that can be very singular. The ones that we are looking are smooth, but several branches. And here is one branch, but very singular. But what they have done is somehow, is again geometrically not clear what is happening. They give this classification, they got all the analytic invariants, but it's somehow a mystery. Why these invariants? At this moment, one student, Ociel Gomez, is trying to get those invariants. He has succeeded for the first invariant, the Zariski invariant that is called, for one branch. So he has already succeeded to give a geometrical meaning, and this geometrical meaning is to put inside the diacritic foliation that curve, the curve, and look to the blow-ups and to analyze what is happening. So the program that we would like to do with Ociel, Jessica Jaures, Felipe Cano, and myself, maybe we're inviting also Boronin, is to to use both approaches. That is several branches and a branch that goes far. And from there, trying to succeed to give an answer to Zariski's problem, Zariski's question about analytic curves. So, well, I don't know, I still have some time?
No.
15 minutes, okay. Well, let me then talk very briefly about a problem that goes out from complex situation, but is very near from all these constructions. And it's also a work with Jessica Jaures. You maybe have heard about Chen theorem. The setting is the infinitely differentiable vector fields. Chen's theorem is Chen theorem says the following: if we have two vector fields, let me put it two vector fields like this, Ax plus higher order terms, that is formally equivalent to other vector field W plus tilde. These are different vector fields that are formally equivalent. That is, we can send one to the other by formal changes of variables. Then, if the eigenvalues are hyperbolic collection of eigenvalues, of A, then both vector fields are C infinity analytically equivalent locally. All this is local. Oh. Yes. This has to deal with flat functions. The problem is to deal with flat functions. So with Jessica, we asked ourselves about an analog of Chen's theorem, but without linear terms. So it in the same setting that we say things about the analytic invariants, we wanted to solve this problem. So for this case, of course, Chen's theorem is in Rn, in a neighborhood of the singular point. In our case, without a linear part theorem, we deal with vector fields only in R2. So it's X in R2, 0, and we have two vector fields that are given by, I will put xy, are given as before by series of analytic vector fields, of differentiable vector fields, smooth vector fields, that have P, N, Q, N as principal part. They are smooth, but they have this principal part. And W, P, N tilde, Q, Q tilde, with the principal part Pn, Qn. The same principal part. So what we could prove is that if they are formally analytically equivalent, formally equivalent, then they are smooth equivalent, but we need to avoid when we blow up. Now when we blow up the singularity, now is the real case, we will have a Möbius strip. We will have here the, we'll have here the singular points. If we complexify, there are other singular points here, complex roots that give singular points, but we don't look to them. We know that they are there, but we don't look to them. We just look to the singular points here. And what we avoid in the hypothesis is to have nodes that are contiguous. If we have here a node, we need to have here a saddle. Saddle. If we again have a node, the next needs to be a saddle. The only thing that makes a lot of noise is to have two contiguous nodes. So we avoid them, and in that case, we can deal with the C infinity classification, and well, is the contribution that we have for things that don't have linear case in the analytic setting and in the smooth setting. So I think it's all that I wanted to say to you.